Okay, so to find the particular solution, you need to know an initial condition. Okay, which we will practice when we actually go over your review and everything. But they have to tell you something or else you can't find that C to begin with. Okay? Okay, also remember that as far as units go, okay, if you have the integral of dq dt from A to B, remember that that represents the change in quantity Q over A to B. So remember that an integral measures how much something changed. We're going to do two specific ones because they have a lot to do with position and velocity. Those are the only two, though, that we're going to talk about. Okay, if you integrate velocity, remember that from A to B, that is the displacement. Okay, you can put in parentheses, that's the change in position. And then what about if we put bars around it? Do y'all remember what that changes? Still starts with distance. Okay, good. If you integrate from A to B, oops, I forgot the other half of my bar. Okay, if you integrate absolute value of velocity, that's the distance traveled. Okay. Okay. All right, we're going to do a little bit of our area properties. Okay, so we'll do these down here. Remember that the integral from A to B of f of x is the exact area between f of x and the x-axis on A to B. Now let's talk about the actual integral. So remember, area is always positive, but remember that if you integrate a function that is below the x-axis, how does your integral come out? If it's below, negative. What about if it's above? Positive. Okay, so I'm going to put a little star here. If your area is above, then the integral is going to come out to be positive. And if your area is below, then your integral is going to be negative on that interval. So you calculate those areas, but remember, you have to keep some sort of direction with them by counting it as either positive above or negative below. Okay, then we're going to throw a couple of those formulas that we talked about the day that we covered this on here. The first one is if you integrate from A to A, what is it? 0. Because remember, if you start shading at A and stop shading at A, then you didn't shade anything, right? Okay, the second one, if you integrate from B to A, okay, notice that your endpoints are actually backwards from the direction that they should be. What do you do to your sign? You would, okay, so you would flip it and then put a negative in the front. So you would find your actual area and then just change the sign. Now, think about it. If your area was already negative, but then it was also backwards, those double negatives are allowed to cross out just like they would with normal numbers. Okay, and then the last one would be if you're integrating from A to B and you have a constant. Remember that you're allowed to take that constant k and you're allowed to pull it to the outside of the integral right here. So it would be k times the integral from a to b of f of x dx. Okay? Alright, if you will next flip over to the back, we're going to do Riemann sums and trapezoidal sums. So last week, remember, we talked about Riemann sums, left, right, and middle, and then trapezoids, I think, is what you missed on Thursday. Okay? Okay. So we'll do Riemann sums on the top. Okay, remember sometimes it's called a Riemann sum, so if you ever hear that somewhere when you're talking with your friends, it's the same thing. Okay, and it is an estimation technique. For non-geometric area. It is an estimation technique for non-geometric areas. Now, we are only going to write out a left one because I don't want to do a gazillion of these. Okay, you should hopefully get the idea. But remember that the integral from a to b of f of x dx is approximated by, remember, not equal to, because it's not the exact area. Okay, but it's an estimation. And then you would do f of x1 times the width of that subinterval plus, and then f of x2, and then the width of that subinterval. And then f of x3 times the width of that subinterval plus ... Okay, now just to make that formula less ugly, okay, I'm going to point out that remember that each one of these is an x or a y that I just underlined. Those are all what? Y value in your life? Or do you just not remember this at all? Or you just don't feel like talking? Okay, coming back a little bit? Okay. So remember that each one of those is just a y value, and then what does delta x stand for? Okay, the change in the x's. So like if I went from 3 to 10, you'd see how far that was, okay? So I'm going to put like a little arrow here. Remember that delta x is how wide the subinterval is. Okay, delta x stands for how wide the subinterval is. Now, does it have to be the same for all your rectangles? No, and so that's why you want to make sure. Now, if it is the same, do you remember your shortcut? You can pull the delta x out to the front. Okay? So I'm going to put equal delta x shortcut. Okay, remember that if your delta x is always the same, you're allowed to pull it out. And then just add up your f of x1 plus f of x2 plus f of x3 plus ... But remember that you can only do that if your width is constant the whole time. Now, just for some quick little shorthands, if you are doing a left Riemann sum, which y value gets skipped? The first one or the last one for a left Riemann sum? Okay, very good. So I'm going to put that on here. If it is a left Riemann sum, that's left RS Riemann sum, write that out if you think you might forget. Okay, you are going to skip the last y value. What about if it is a right Riemann sum? Who gets skipped? Okay, so right Riemann sum, you are going to skip the first y value. And if it is a midpoint, does anybody get skipped? No, but what do you have to remember to do when you set up your intervals? Do you remember you have to skip one so that you're leaving a y value in the middle? So you're going to have to skip a y value each subinterval. And we will do examples of these just to remind you, but just for you to have the shorthand on here. Then also remember, another thing that you can check is if your area is too big or too small. And remember, you would just have to draw a picture for that. Okay? All right, what was the other rule that we learned? Besides using rectangles, what other shape can we use?
Trapezoid.
Okay, trapezoidal rule. And remember that this is also a way for you to estimate those non-geometric areas, but this one tends to be a little more accurate. You would have your integral from a to b, f of x dx, approximated by, because remember it's not exact, and you would be adding up the area of multiple trapezoids based on that shape. So it would be 1/2 y1 plus y2 delta x plus. Then your next trapezoid would be y2 plus y3. Then the delta x associated with that trapezoid. Remember that delta x is still your width. y1 and y2 are your bases, but they're vertical. Okay, that's why we're calling them that. Okay, plus 1/2 y3 plus, ooh, that doesn't look like a 1/2. Make yours look more like a 1/2 than that, okay? Oh, it just looks worse. I can't even write. It's fine. Okay, plus dot dot dot. Now, if you have equal subintervals, do you remember we noticed a pattern that allowed us to condense a lot of that formula? Okay, so if you have equal delta x's, this is your shortcut. Remember, only if they're equal, you can take out the 1/2 and the delta x. And then do you remember what you do with your bases? The first one and the last one are only in there once, but do you remember all the middle ones get doubled? Okay, so you'd have y1 plus double y2 double y3 plus dot dot dot, and then only one yn, where n we would say is the last one. And remember that we talked about why that is. If you want to go back and look at the notes, or I'm happy to explain it to you again. Okay, but that's the general idea. Now, if you want to know if a trapezoid is an over or an underestimate, okay, remember that it depends on concavity. So over or under estimate depends on concavity. So I want you to draw a concave up graph on this side. Okay, I'm just going to draw it like that. And then I'm going to draw a concave down graph on this side. So this is CCU for concave up. This is CCD for concave down. And then what I would do on the AP test or on any other test is I would just draw a little sample, okay, pick like a little section of your graph, and then draw a trapezoid. How does the area of my trapezoid compare to the actual area under my curve? Is it too big or too small here?
It's too big.
It's too big, because remember, the integral is this exact area, right? So my trapezoid is just a little bit too big. Now, what's going to happen on this one if I pick any y values and I draw my trapezoid in? How does my trapezoid compare here? It's just a little bit too small. Okay, so in this case, the trap is an over estimate. And in this one, your trap is an under estimate. Okay? Because remember, you're trying to estimate that perfect amount of area. So your trapezoid's never going to hit it exactly perfectly. It'll always be a little too big or a little too small, and it's concavity that determines that. Okay. Okay, that being said, you have your cheat sheet. You get to use it on your test, which is on Monday. So over the next 2 days, we're going to go over some questions from your review and take little mini quizzes, okay? So why don't you, on your review, rewrite for me number 1. I'm going to tell you which ones to rewrite. Number 1, number 3, and number 7, and number 10. 1, 3, 7, 10. 1, 3, 7, 10. Okay, and just give a shot on just the rewrite step. And actually, if you want to throw in number 13 too. So remember, it has to be a power. So you have to try to fix it so that it looks like a power. Anybody need to take a picture of this? You need. Okay, number 1, I'm going to do it wrong. Tell me what I did wrong. Okay, I'm like, oh, the 8x is on the wrong part of the fraction. So I'm going to write it like this. 8x to the negative 3. Boo. Maybe some of you did that. Okay, what did you do? What should you not do with that? Can't bring the 8 up. Where would you have to leave the 8? On the bottom. So for your rewrite, oh gosh. Sorry about that. Okay, you'd have integral of 1 over 8. That constant has to stay, but then your x would be to the minus 3. Okay, then on your second term, minus 2, x to the negative 2. Okay, then remember the power rule that we learned is the opposite of the derivative. You add 1 and then divide. Okay, so if I'm doing this one, what's negative 3 if I plus 1 to it? Negative 2. So that's going to be x to the negative 2. And then if I already have a 1/8 and I divide by negative 2, that's the same as timesing by negative a half. What do we do with those fractions? Remember how to multiply fractions? Straight across the top, straight across the bottom. So half of an 8 is a 16th. Does that make sense? Okay, so I'm going to write it up here at the top. So negative a 16th. And then if my x is to the negative 2, I'm just go ahead and write that on the bottom. Okay, next term, I had a negative 2, so I'm going to have to add 1 to it, plus 1. What is negative 2 plus 1? X to the negative 1. Then I divide negative 1 with the negative 2, it switches to a plus 2, plus c. Then from there, I'm going to take my x down, so it'd be plus 2 over x plus c. Make sense? Good? Okay, number 3, how do we rewrite if we have one thing on the bottom? Split it up. Very good. So I would have x to the 4th over x plus 1 over x. And then if it's x to the 4th over x, what are you allowed to do? 4x is on top, 1x on bottom. They're going to cross out. How many are going to be left over? X cubed. Now, for my 1 over x, I'm going to leave it. Does anybody remember why? ln x. Very good. So for this part, I'm going to do power rule, but then that one's going to be an ln. So remember, you add 1, so x to the 4th. Then I have to divide by 4, so it's a 1/4. If you want to put a little star there, okay, remember, the power rule will not work on x to the negative 1. Because if you add 1, you get x to the 0, and then you're not allowed to divide. What step did you use on number 4 to make that no longer a product?
No.
Distribute. Boom, boom. Put little arrows to help yourself remember. Okay, and let's go to number 7. Okay, what is the square root of y the same as? Y to the what? To the 1/2. Okay, good. So I have the integral of y to the 3 times y to the 1/2. Okay, we have to put those y's to have the same base. So think back to algebra 1. What do you do with exponents when you're multiplying their bases? Remember? You add them. So I want to know, what is 3 plus 1/2? Okay, well, what is 3 as halves? Says that weird. 6 halves, right? 6 divided by 2 is the same as 3. So what is 6 halves plus 1 more half? Y to the 7 halves. And now we can do our antiderivative based on our normal power rule. So when you're multiplying bases, you add the exponents, and now we're just going to do our normal power rule. So I'm going to add 1, which is the same as 2 over 2. What is 7 over 2 plus 2 over 2? 9 over 2. And then if I have to divide by 9 over 2, that's the same as multiplying by the reciprocal, which would be what? 2/9 plus c. Okay, you can use that one to help you on number 5. Go ahead and do your rewrite on number 5. How would you do that cubic root of x squared? How would you rewrite that first term there? Which one goes on top? 2. X to the 2/3. And remember that you would only turn that exponent negative if it were like in the denominator, if it were like part of a fraction. Number 10, what would we need to do there? And can you all do this one? You good? Yeah, okay. We can check it tomorrow if you can't get it. Okay, number 2, take that 2 out to the front. And now it's the same as 2 integral 1 over x. Remember, you're always allowed to take that constant out to the front. And now that it's 1 over x, that should look familiar. What's that? Good, so that would be 2 ln x plus c. And a lot of times I don't say absolute value, but remember those bars do go there. Yes?
When you move the 2 out, does it matter if you move the 2 out past the integral or inside?
It doesn't matter. You could put it in either spot and it would be fine. Number 13. Okay, if you have some stuff on the outside of parentheses, we're going to do the same thing we did on number 4. Draw your little arrows. We're going to multiply. So my first integral is going to be secant theta tan theta. And my second integral, if it's secant times secant again, how could I write that? Secant squared theta. Okay, now when you do this, you got to pull out that pink sheet. Okay, and I see that doesn't look like anyone has it out, but don't worry, I have one right here. Okay, we want the integral of secant tan. Where's the integral?
16.
Okay, rule 16, look at it. What's the integral of secant tan? Secant. Now, what's the next thing on your sheet? Secant squared, right? Okay, secant squared, boom. What's the integral?
Tan.
Tangent. Okay, so you just use that rule sheet, or remember, it's your derivatives backwards. So this would be secant theta, tan theta, plus c. Good job. Make sense? All right. 18. 18 and 19, if you're asked to solve the differential equation, that means that you have to get back to the original function. So, do we want to do it, or do y'all remember how to do it?
Which one?
Either one. Do we want to do one of them?
Oh, 18.
Yeah, 18 or 19. Okay, let's do 19. Okay, so first thing that you should notice is that this is the second derivative. And so if I'm trying to go back to y, I'm going to have to do that integral crap twice. Yeah, we on the same page about that? Okay, so start off integral. Boom, boom. What is the integral of d squared y dx squared, the second derivative? dy dx. Okay, and then think about your snow cone. If that's a 3 sine x, snow cone. Yeah, we go up from sine. We'd be back at the bottom of the ladder at negative cosine. So negative 3 cosine x. And then am I going to use the 5 or the 10 for this? Why the 5? Because it's an f prime, and this is a dy dx. So these are both first derivative pieces of information. So 5 is the answer when I plug in negative 3 cosine 0. Okay, does cosine 0 cross out? No, what is it? 1. So I'd have 5 equals negative 3 times 1 is just negative 3 plus c. What is my c? 8. And then I would come back right here to where my c was. I'm going to cross it out and just squeeze in a little 8 there so I don't have to rewrite the whole thing. Okay, so cross it out, put in 8. So this is now my first derivative. Now, to get from my first derivative to my original function, I'm going to have to do that one more time. So do your first step. So you're integrating on both sides. So integral of dy dx, then integral of the 3 cosine stuff. What is the integral of dy dx? Because I want to know. Get it? It's y. Okay. That's a fail. Okay, so the integral of dy dx is just normal y. Okay? And then integral of negative 3 cosine. Think snow cone. Negative 3 sine. What's the integral of 8? 8x plus c. And then from there, what do we know? F of 0 is 10. So 10 is the answer when we plug in 0. And is sine of 0 going to cross out?
Yeah.
Yes. Sine of 0 is 0. That term crosses out. Your other 0 crosses out. So really c is just 10. And at that point, you have your entire equation. So y equals negative 3 sine x plus 8x plus 10. Boom, done. Okay? Great. All right, turn the page. Okay, we have some position, velocity, and acceleration. Do we need to go over that? Or y'all feel good about it? Feel good about it? Okay. And remember, we can always come back to it. If you end up trying it and it's a fail, that's okay. Do we want to do one with all the sums and stuff?
Where?
Like number 27?
Yeah.
Look, this one. Helen says, yeah, she's on the wrong page.
No.
Oh, you
right here.
thought you were looking at totally the wrong page. Okay. Alright, you have the velocity of a rocket given at certain values. What are we measuring our velocity in?
Meters per second.
Meters per second. Part A says to find average acceleration. We have velocity. We have to find acceleration. Is that a derivative or an antiderivative?
Derivative.
That's a derivative. There are two types. You can do the average rate of change or the slope at that one point. Can we do slope if we don't have an equation? No, so it has to be what? Average rate of change. Also, the A stands for average, okay? So, average rate of change over the first 12 seconds would be from 0 till 12. So, I would find the velocity at 12 minus the velocity at 0 over 12 minus 0. Now, it says to include units in your answer. What is velocity measured in? Meters per second. What's time measured in on the bottom? Seconds. So what should your answer be? Okay, meters per second squared. Okay, you can do that. Part B. We want the distance traveled by the rocket in the first 12 seconds. Now notice we're cutting off at 12. Okay, so make sure that you're noticing that. Okay, it says, is your approximation over or under? So how do I denote the difference between distance traveled and displacement? Absolute value. Now, technically, let's pretend this was the AP test. If you didn't put it and all your y values are positive, would you be counted off? Probably not. Okay, 0 to 12. What are the details of our sum? Which side are we going to use?
Left.
Okay, a left Riemann sum. So remember, look back at your orange little cheat sheet if you need to. For a left Riemann sum, do we skip the first one or the last one? The last one. So look, I'm going to, for fun, cross out 12 and pretend like I'm not going to use it. Okay, from 0 to 3, how wide is it? 3. And what is the left y value? 20. So it would be 20 times 3 plus. Okay, for my next one, I already used 20. Now I'm on 22. The distance with that would be from 3 to 5. How wide is that? So 22 times 2. Next one, I'm using 29. What's the distance from 5 to 9? 4. So 29 times 4 plus. And then last one, from 9 to 12, how far is it? 3 units. My left y value is 38. Now notice, every time, this is the y value, and this is the delta x, or the distance, the width across that subinterval, over the subinterval. Okay, y'all remember doing that? Okay, next question. In the same part, is your estimation under or over? Look at your y values. Are they getting bigger each time or smaller each time? Okay, every time they're getting bigger. So I'm going to draw a graph that's going uphill. I'm going to pick any little chunk of the graph that I want, but I'm going to use the left endpoint to determine how tall it is. So this is the left side. How does the area of my rectangle that I picked compare to the actual area on that subinterval? Too big or too small?
Too small.
Too small. So this would be an underestimate. Okay? And then when it says justify, you would say maybe because V is increasing. So the left endpoint is always the smallest. On each subinterval or something like that. Okay, but you would draw your picture. A lot of times they don't really ask you to explain those two in depth because it is kind of like either you know it or you don't. Okay, your velocity is increasing. That means that your left endpoint's always the lower side versus your right endpoint is the upper side. Okay, next one says we want a right Riemann sum. What happens on a right Riemann sum? Who do we skip? Okay, skip the first y value. Okay, so my integral is approximated by 0 to 12 v of t dt. Okay, what's my first width from 0 to 3? How far is that? 0 to 3. 3, and what is my right endpoint between those y values, 20 and 22? I would pick 22. For my next one, from 3 to 5, how far is it? 2, and my right y value would be 29. My next one from 5 to 9 is a distance of 4. My right endpoint would be my 38. And then from 9 to 12, that's a distance of 3. What is my right endpoint? 42. And remember, I crossed it out last time, but I'm using it this time because it's the right. Okay? Now, think about, I'm going to just scribble on this same picture. Or no, maybe we'll do another one. Okay, make your graph still go uphill, but I want you to pick any subinterval and use the right endpoint to determine how tall your rectangle is going to be. So, cut it here and here. This is my right side. I would be cutting over the curve. Is that too big or too small for my area? It's a little bit too big. That makes it an overestimate. Okay, then it says justify, you would say, because v of t is increasing. So the right endpoint is the biggest. On each subinterval. Okay, part B, we're doing a midpoint Riemann sum. How far are we going to integrate on this one? Look at your time. In the first what? 20 seconds. So what's going to change on my integral symbol? Instead of going 0 to 12, I'm going from 0 to 20. And then remember, for a midpoint, I'm going to put a little star here. Remember, you have to skip one. Skip a y value each time. Okay, so I'm going to come up to my graph. I'm going to mark some stuff out. Okay, and then I'm going to come back to down here. So if you miss something, just hang on. So for midpoint, okay, look at your table here. I'm going to go from, we'll go orange, from 0 to 5. And then what is the y value in the middle, the midpoint that I'm skipping? 22. Then from 5 to 12, what's the midpoint that I'm skipping? 38. And then from 12 to 20, I'm skipping 49. Now remember, your delta x is going to go from 0 to 5 here. How wide is that? 5. Then from 5 to 12, how wide is that? Because remember, I'm skipping this one. Delta x is 7. And then from 12 to 20, how far is that? 8. But remember, what am I multiplying? The delta x and the middle y value on that subinterval. So, right on your paper, it'd be 5 times 22 plus 7 times 38 plus 8 times 49. So, approximated by 5 times 22 plus 7 times 38 plus 8 times 49. Can you tell if a midpoint is over or under? No. Because remember, a little bit's too much, a little bit's too little, and they kind of cross each other out. Okay, last one is your trapezoidal rule. Okay.
What's the thing in the middle?
Oh, it should have been v of t. For the last one, do we have the same delta x every time?
No.
If only, but we don't. So, I'll do the first couple of them with you, and then I'm going to stop. Okay? Approximated by 1/2. What are my first two y values that are my bases in my table? 20 plus 22. And then look at their x's. How far apart are those y values? From 0 to 3, that's a 3 distance. Plus, my next trapezoid, 1/2 is part of the formula. My second bases would be 22 plus 29. And then remember, you have to look at their x's, how far apart they are. So from 3 to 5, how wide is that subinterval? 2. Okay, set up the next one. And then if you got it, then we'll move on. Okay, next one, you should still have a 1/2. Your y value should have been 29 plus 38, and then the delta x from 5 to 9 would have been a width of 4. Got it? Okay, plus, and then you can finish it later for fun. Okay, last one we'll go ahead and set up just in getting you ready for your mini quiz tomorrow. Is going to be the one with all the area pictures somewhere. Here. Boom, right there.
Is that a mini quiz for tomorrow?
Your mini quiz for tomorrow is going to have a picture just like this where you're finding area, and then it's going to be antiderivatives. Those two things. Okay? So why don't you just do the left side? Boom, 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 boom. And they're all just little areas. So where should you be shading on that first one? Between what two numbers? -4 to -2. And then if you shade in your picture, what shape is that? Trapezoid, but remember your bases are up and down. So it would be 1/2 base plus base times height. How long is this first base? 1. How long is this base? 3. So 1 plus 3. And then how long is the height? 2. So 1 plus 3 is 4 times 2 is 8. Cut it in half is 4. Now, how is F different? Look at the one right next to it. Almost the same, but two things are different. Okay, it's flipped, and what's in the middle?
6.
The 6. So remember, I can pull that 6 to the outside. I'm just going to cross it out and move it. And then if my endpoints are backwards, remember you change the sign. So if this integral is 4, what's this integral? -4. So it's 6 times -4, which is -24. Okay, next one from -4 to -1. What additional area am I going to include on my picture if I shade from -4, which is here, to -1, which is here? You have that little triangle. Now, we already found this area. It was 4, so I'm just going to mark that in my picture. Okay, find the area of that triangle. It would be 1/2 base times height. 1/2, my base is 1, my height is 3. So that would just be 3/2. So what would my area be in part B? It would be 4 plus 3/2. Can I leave it like that?
No.
Okay. So I can leave this, but I don't want to forget about the 6. That's right. So for free response, that would be acceptable. And then just keep that 6 right there. G should be easy. What's G? Integrate 1 to 1. 0, because you'd have no area. Okay, for C, from -1 to 1, what shape would you be shading? From -1 to 1. Very good. From -1 here all the way to 1 here. Okay, that would be a circle. How do you find the area of a circle? Pi r squared, but then don't forget to cut it in half. So if my r in that case, how long is my r? My diameter is 2. What's my radius though? 1. So it'd be pi times 1 squared. That'd just be pi. Cut it in half. It'd be, oops, pi halves. Positive pi halves? Why would it be negative? Because it's below. What if it was also backwards? Then it would be back to positive. Okay? Does that kind of get you started there?
Yeah.
Okay, the bell's going to ring in a minute, so I don't want to make you scramble. But okay, so tomorrow, antiderivatives and area. You'll be able to do those two things. You're going to do great. Okay? So great. Valerie, did we go over the sums? Or were you confused on that? I can't remember what we got. We didn't get to that when you and me were going over stuff, did we? Did you kind of pick up on it? A little bit or not really? How did it remember? Okay. When do you want to work on it? Now? Oh, great. Thanks, Emily. Y'all have a good day.
You too.
Thanks.